Hello there, and welcome to the Sleepy Science Channel. I'm glad you found your way here, because tonight we'll be exploring some of the greatest mysteries in all of physics. Quiet questions that drift at the edge of our understanding and tug, gently, at the fabric of what we think we know. At this very moment, the night sky is full of countless stars, galaxies, and untold wonders. Their light has traveled for millions, even billions of years, crossing unimaginable distances just to reach you in this sleepy moment. It's humbling when you think about it. For all our technology, all our theories and observations, we still don't know what most of the universe is made of. We've mapped the galaxies. We've measured the age of the cosmos. We've even traced the whisper of the Big Bang. But beyond all of that, something else remains. Something vast, invisible, powerful, and largely unknown. Dark matter, dark energy, forces and substances that shape the cosmos on the largest scales, bending galaxies, accelerating expansion, and rewriting the boundaries of what physics can explain. We can see their effects. We know they're there. But we don't know what they are. And that's where we begin. All across the universe, galaxies spin, vast wheels of stars and gas whirling through space. But when astrophysicists measured how fast they rotate, something didn't add up. The stars at the edges were moving far too quickly. Based on the gravity from visible matter alone, stars, planets, gas, those outer stars should have been flung into deep space. Instead, they stayed in orbit, as if held by some invisible glue. That glue, it seems, is dark matter. We call it dark not because it's sinister, but because it doesn't emit, absorb, or reflect light. It's invisible to our eyes, to our telescopes, to every known form of electromagnetic detection. And yet, we know it's there, not by seeing it, but by seeing what it does. It tugs on galaxies, bends light around clusters, and sculpts the shape of the universe on its grandest scales. It outweighs all the normal matter we can see by a factor of 5. In a very real sense, dark matter dominates the cosmos. We just don't know what it is. The story begins in the 1930s with the Swiss astronomer Fritz Zwicky. While studying the Coma cluster, a group of galaxies bound together, he noticed the galaxies were moving so fast they should have flown apart. But they hadn't. He proposed that some unseen mass, which he called dark matter, must be holding the cluster together. His ideas were dismissed for decades. But in the 1970s, Vera Rubin and Kent Ford observed the rotation curves of individual galaxies and confirmed the same strange pattern. Outer stars were moving far too fast. The gravitational pull of visible matter alone couldn't explain it. Since then, galaxy after galaxy has shown the same signature. Flat rotation curves, refusing to fall off with distance as Newtonian physics would predict. It's as if each galaxy is embedded in a vast, invisible halo, a cocoon of mass we cannot see, but must account for. Even when galaxies collide, the dark matter doesn't behave like gas or stars. It passes through, undisturbed, like a ghost. The Bullet cluster, a pair of merging galaxy clusters, provided one of the most striking pieces of evidence. Using gravitational lensing, astronomers mapped where the mass truly was, and it didn't match the glowing clouds of visible matter. It matched the dark. Gravitational lensing, the bending of light by mass, has become one of our most powerful tools for detecting dark matter indirectly. When light from a distant galaxy passes through a cluster on its way to Earth, the cluster acts like a lens, warping the image. By analyzing these distortions, we can map the mass distribution in the foreground, even if we can't see it. Again and again, These maps reveal more mass than we can explain with stars and gas alone. And yet, despite this overwhelming indirect evidence, dark matter continues to evade direct detection. We can describe its effects with precision. We can calculate how much of it there must be. But the particles themselves, the fundamental stuff of dark matter, remain a mystery. They do not seem to interact with ordinary matter through any force except gravity. And even that, only weakly. So what could it be? Over the past few decades, physicists have proposed a number of candidate particles to explain dark matter. One of the earliest and most studied possibilities is the WIMP, the weakly interacting massive particle. WIMPs are hypothetical particles that interact via the weak nuclear force, but not the electromagnetic force, which would explain their invisibility. Their predicted mass and properties arise naturally in many extensions of the standard model, including supersymmetry. For years, WIMPs were the leading contender. Entire underground laboratories were built to catch them. Massive detectors shielded from cosmic rays and background noise, waiting for a rare collision. But none came. As experiment after experiment returned null results, attention turned to other candidates. One is the Action, a lightweight, ghostly particle first proposed to solve a problem in quantum chromodynamics, the theory of the strong force. Actions are incredibly light, but could exist in such enormous quantities that they add up to a major source of mass. Specialized detectors are now tuning in to the narrow frequencies actions might produce as they convert into photons in a magnetic field. Other ideas go further afield: sterile neutrinos, hidden sector particles, even primordial black holes. Some researchers suggest dark matter might not be a particle at all, but a modification of gravity, an approach known as modified Newtonian dynamics. And yet, none of these have yet answered the riddle. What dark matter is made of remains uncertain. But what it does, how it shapes the universe, is better understood. In fact, without dark matter, the cosmos as we know it couldn't exist. In the early universe, shortly after the Big Bang, ordinary matter was too hot and energetic to collapse into structures. It interacted strongly with light, which kept it from clumping. But dark matter, unaffected by radiation, could begin to form dense regions even in the earliest moments of time. These became the gravitational wells into which ordinary matter would eventually fall. In this way, dark matter served as scaffolding. Tiny fluctuations in the density of dark matter provided the seeds around which galaxies and clusters could grow. Simulations of cosmic evolution show this vividly. When dark matter is included, the resulting web of large-scale structure, filamentary networks of galaxies and voids, matches what we see in the sky. Without dark matter, the universe looks nothing like it does. There would be no galaxies, no clusters, no stars, and very likely, no us. It's not just about formation either. Dark matter still plays an active role in holding galaxies together. Its presence explains the stability of spiral galaxies, the shapes of galaxy clusters, and the patterns we see in the cosmic microwave background. These fingerprints, subtle ripples in ancient light, match the predictions of a universe where dark matter outweighs normal matter 5-to-1. It's not just a patch for missing mass. It's woven into the very blueprint of cosmic evolution. And yet, we still haven't found it. Not directly, not unmistakably. The scaffolding is there, holding up the cosmos, but the beams remain invisible. So why can't we find it? Despite decades of effort, not a single confirmed dark matter particle has been observed in a laboratory. The problem is one of interaction. Ordinary matter reveals itself in countless ways, through charge, light, heat, friction. But dark matter seems to interact only through gravity, and perhaps the weak nuclear force. That makes it extraordinarily hard to catch. Most particles pass through our bodies by the trillions every second, unnoticed. Dark matter does the same, but without leaving a trace. Experiments designed to detect WIMPs, for example, rely on a dark matter particle occasionally striking an atomic nucleus and transferring a tiny amount of energy. These detectors are buried deep underground, in old mines, mountain caverns, shielded by rock, to block background noise. But even with extreme sensitivity and years of observation, the results remain frustratingly empty. Other methods, like looking for dark matter annihilation signals in space, or its production in particle accelerators like the LHC, have also returned no clear evidence. It's possible we've been looking in the wrong place, or for the wrong thing. Part of the difficulty may lie in our assumptions. Many early searchers were guided by elegant theories like supersymmetry, which predicted certain kinds of particles in certain mass ranges. As those are ruled out, the parameter space widens. Dark matter could be lighter, heavier, colder, more diffuse, or something stranger altogether. It may not exist in the form of particles at all. It may behave like a field. It may interact with itself in ways we haven't imagined. Or, more radically, perhaps our understanding of gravity breaks down on large scales. Each path leads deeper into uncharted physics. And that's what makes dark matter so profound. This isn't just a case of a missing piece. It's a sign that our entire picture of matter, of what the universe is made of, may be incomplete. The standard model of particle physics is one of the most successful theories in science, but it doesn't include dark matter. Whatever dark matter is, it lies outside our current framework, which means it isn't just a problem for cosmology, it's a doorway to new physics. If we can understand dark matter, we may open the door to entire realms of particles and forces we've never seen. Our current view of matter is based on a few familiar building blocks: protons, neutrons, electrons, and their interactions through 4 known forces. But nature may be far more diverse. Dark matter could be the tip of an unseen sector of physics, a shadow world with its own particles, its own symmetries, its own dynamics. This possibility reshapes how we think about the cosmos. The matter we see, the stars, the gas, the planets, even ourselves, might be just a thin glaze on the surface of a much deeper reality. A kind of luminous icing floating on a dark ocean. We spent centuries studying the visible universe. But if dark matter truly dominates it, then most of the universe is still invisible, not just in appearance, but in essence. And that's humbling. It suggests that what we call normal matter may not be normal at all, just familiar. In recent years, the search for dark matter has grown more creative and more urgent. New generations of detectors are pushing sensitivity to unprecedented levels, and these experiments are probing weaker interactions and lower masses than ever before. Some now target ultralight dark matter candidates using resonant cavities, superconducting circuits, or even vibrating crystals. Others look to the skies. The Fermi Gamma Ray Space Telescope scans the galactic center for annihilation signals, while gravitational wave detectors explore whether dark matter could consist of tiny black holes from the early universe. Still others turn to quantum technologies, using cold atoms, interferometers, or nanoscale sensors to detect the faintest of tugs. But with every new approach comes more complexity and more questions. What if dark matter isn't just one thing, but many? Could it consist of multiple components, like ordinary matter does? Might it interact with itself, forming invisible structures, or dissipating energy in ways we haven't yet detected? And perhaps most troubling, what if dark matter doesn't exist at all? If the evidence we see is pointing not to missing mass, but to a misunderstanding of gravity? Modified gravity theories like MOND or emergent gravity offer alternative explanations, though they remain controversial and incomplete. The truth is, we don't yet know. And that uncertainty, while frustrating, is also what makes this search so powerful. Because to solve the dark matter mystery is to confront the boundaries of knowledge itself. We're no longer just weighing galaxies or mapping halos. We're testing the limits of our theories, our tools, and our understanding of what the universe is made of. And in doing so, we're reminded that the cosmos still holds secrets, vast, invisible, and waiting. It might be hard to believe, but the story gets even stranger. In the late 1990s, two independent teams of astronomers were studying distant supernova, brilliant stellar explosions that serve as cosmic mileposts. They were trying to measure how quickly the universe's expansion was slowing down. Gravity, after all, pulls things together. So the assumption was that, over time, the expansion from the Big Bang would be decelerating. But when the results came in, the astronomers were stunned. The supernova were dimmer than expected, farther away than they should have been. The universe wasn't slowing down. It was speeding up. This discovery, that cosmic expansion is accelerating, shook the foundations of cosmology. Something was pushing space itself to stretch faster and faster, defying gravity's pull. But what could it be? The simplest explanation, first proposed by Einstein and then discarded, was the cosmological constant, a kind of intrinsic energy of space. But even that idea raised thorny questions. If space contains energy, how much? Why that amount? And where does it come from? Lacking answers, physicists gave the phenomenon a new name: dark energy. But like dark matter, it remains unseen, known only through its effects. At first glance, dark energy and the cosmological constant might sound like two names for the same thing. But there's an important difference. The cosmological constant, denoted by the Greek letter lambda, is a fixed value, a uniform energy density that fills space evenly, never changing over time. It was introduced by Einstein in 1917 as a fudge factor to keep the universe static, later discarded when the expansion of the universe was discovered. But now, in light of the accelerating cosmos, it's returned, not as a mistake, but as a serious contender. Dark energy, by contrast, is a broader term. It encompasses the cosmological constant, but also includes more exotic possibilities. What if this energy isn't constant? What if it evolves over time? These alternatives fall under the umbrella of dynamic dark energy, with one of the most studied models known as quintessence. In these theories, dark energy is a field that varies across time and space, more like the scalar fields used in inflationary cosmology. Depending on its behavior, it could lead the universe to expand forever, to rip apart, or to slow down again in some future epoch. But no matter the model, the effect is the same. Dark energy dominates the large-scale behavior of the universe. About 68% of the universe's total energy content appears to be in the form of dark energy. It doesn't clump like matter, and it doesn't dilute as space expands. Instead, it exerts a kind of negative pressure, a repulsive force woven into the very fabric of space-time. This subtle yet persistent push affects the universe's expansion rate, the growth of cosmic structures, and even the ultimate destiny of everything we know. Over billions of years, dark energy has reshaped the cosmos. In the early universe, matter, both normal and dark, was the dominant force. It pulled together clouds of gas, forged galaxies, and carved the great cosmic web. But as the universe expanded, the density of matter decreased, while the influence of dark energy remained constant or even grew. At a certain point, around 5 billion years ago, dark energy overtook matter as the driving force of cosmic evolution. Since then, galaxies have drifted farther apart, the expansion has accelerated, and the structures of the universe have begun to freeze into place. This acceleration means that distant galaxies are now receding from us at ever-increasing speeds. Eventually, regions of space beyond a certain distance will move away faster than light can bridge the gap. Those galaxies will fade from view, becoming forever unreachable. Cosmic isolation will deepen. In trillions of years, the night sky could grow dark again, not because stars have gone out, but because the universe has expanded so much that light can no longer cross the void. The future may hold not just silence, but solitude on a cosmic scale. And yet, this is only one possible fate based on what we think dark energy might be. The truth is, we still don't know. Is it truly constant? Is it changing? Is it even real? Or a sign that our understanding of gravity needs revision, just as with dark matter? These aren't questions of idle speculation. They cut to the heart of physics, of what space and time themselves are made of. To study something as elusive as dark energy, astronomers rely on the universe itself as a laboratory. Supernova, the massive explosions of dying stars, are one of the most powerful tools. These stellar explosions occur in binary systems when a white dwarf accretes matter from a companion star until it reaches a critical mass and detonates. Because they occur under similar conditions, they have nearly uniform intrinsic brightness. This makes them standard candles, objects whose distances can be estimated by comparing their known luminosity with how bright they appear. By measuring the redshift of these supernovae, how much their light has been stretched by the expansion of space, astronomers can reconstruct how the universe has expanded over time. That's how the acceleration was first discovered. And ever since, these stellar beacons have continued to trace the cosmic expansion, providing key evidence for dark energy's influence. But supernovae are not the only line of evidence. The cosmic microwave background, the faint afterglow of the Big Bang, provides a snapshot of the universe as it was just 380,000 years after its birth. Embedded in this light are tiny fluctuations in temperature, which encode information about the geometry and contents of the cosmos. When dark energy is included in the models, the positions and amplitudes of these fluctuations align beautifully with what we observe. Without it, the picture doesn't fit. Other probes include baryon acoustic oscillations, subtle ripples in the distribution of galaxies, and weak gravitational lensing, where the shapes of distant galaxies are slightly distorted by intervening mass. Together, these methods converge on the same conclusion: the expansion of the universe is accelerating. Dark energy is real, or something that mimics it is. But the what remains unsolved. The leading theoretical explanation, the vacuum energy of empty space, turns out to be deeply problematic. Quantum field theory tells us that even a perfect vacuum isn't truly empty. Instead, it seethes with temporary particle-antiparticle pairs popping in and out of existence. These quantum fluctuations give rise to a non-zero energy density, and in theory, this vacuum energy should behave exactly like the cosmological constant. But when physicists try to calculate how much energy this vacuum should contain, the numbers go haywire. The result is off by a staggering factor, somewhere between 10 to the power of 12 and 10 to the power of 38 times larger than what we actually observe. This discrepancy is often called the worst theoretical prediction in physics. Why is the vacuum energy so small? Why is it not zero? And why is it roughly the same order of magnitude as the matter density of the universe right now? These questions have no satisfying answers. Some physicists suspect an unknown symmetry cancels most of the vacuum energy. Others invoke the anthropic principle, the idea that we observe this value because only universes with similar values can support life. But these are not fully predictive explanations. They are placeholders for deeper insight still to come. In response to this crisis, other theories have emerged. Quintessence models posit a dynamic field, similar in spirit to the Higgs field, that slowly evolves over time. Unlike a constant, its influence can grow or fade, depending on the properties of the field. This opens the door to a wider range of cosmic fates, but also makes the physics harder to constrain. The space of possibilities becomes enormous, and without firm observational handles, many models remain speculative. Still, some may leave signatures, subtle changes in the equation of state of dark energy, or variations in its density with redshift. Future surveys hope to test these. One of the most striking consequences of dark energy is its effect on the geometry of space-time itself. In general relativity, the distribution of energy and matter determines the curvature of space. In a universe dominated by matter, the curvature depends on the total density. If it's high, space curves inward. A closed universe, if it's low, it curves outward, an open universe. But dark energy, particularly in the form of a cosmological constant, changes that relationship. It doesn't clump like matter or dilute as the universe expands. Instead, it acts as a constant outward pressure, flattening space and accelerating time's passage from one cosmic epoch to the next. Observations of the cosmic microwave background, large-scale galaxy clustering, and lensing patterns suggest that the universe is remarkably flat on large scales, precisely what you'd expect in a universe cantor, balanced between matter and dark energy. But it's a delicate balance. Slight changes in the amount or behavior of dark energy would tip the geometry, altering how light travels, how structures grow, and how the universe unfolds. This expansion isn't just a gentle swelling. It rewrites the ultimate destiny of the cosmos. If dark energy is truly constant, then galaxies will drift ever farther apart, stars will burn out, and the universe will grow colder and emptier, a future often called the Big Freeze. But if dark energy strengthens over time, as in some phantom energy models, it could lead to a big rip, where the expansion becomes so extreme that even atoms are torn apart. Alternatively, if dark energy decays or reverses, the cosmos could eventually collapse in a big crunch. The shape of tomorrow hinges entirely on the physics of dark energy, and right now, we are only guessing. To close the gap between theory and reality, physicists and astronomers have turned to a new generation of instruments and surveys. The Euclid Space Telescope, launched by the European Space Agency, is mapping billions of galaxies to chart the expansion history of the universe and the influence of dark energy over cosmic time. The Vera C. Rubin Observatory in Chile, with its 10-year legacy survey of space and time LSST, will observe the entire visible sky every few nights, building an unprecedented dataset of transient Kampir, events and gravitational lensing effects. NASA upcoming Nancy Grace Roman Space Telescope will complement these efforts, using wide-field infrared imaging to detect subtle signatures of cosmic acceleration. Each of these missions is designed not just to confirm the presence of dark energy, but to constrain its properties, to test whether it behaves like a cosmological constant or something more complex. These experiments may help determine whether dark energy evolves over time, whether it clumps in unexpected ways, or whether it connects with deeper layers of particle physics and field theory, still waiting to be uncovered. But for now, many questions remain wide open. What is the true nature of dark energy? Why did it begin to dominate the universe's expansion only recently in cosmic history? Is it related to quantum fields, vacuum energy, or something stranger? Does it point to extra dimensions, multiverse models, or undiscovered symmetries in the laws of physics? Or is it a hint that general relativity itself, the very structure of space-time, needs revision? In many ways, dark energy is not just a phenomenon. It is a boundary, a vast, expanding edge to our understanding. We know it's there. We feel its influence in the motion of galaxies and the dimming of distant stars. But its cause, its meaning, its place in the puzzle of the cosmos, those remain hidden. Black holes are among the most mysterious and extreme objects in the universe. They begin as a consequence of gravity pushed to its limit. When a massive star exhausts its nuclear fuel, nothing remains to resist the inward pull of its own weight. If the collapse is complete, the core compresses beyond all known matter states, forming a singularity, a point of infinite density, where space-time itself breaks down. Around this singularity forms the event horizon, a boundary from which nothing, not even light, can escape. It is not a surface, but a threshold. Cross it, and return becomes impossible. At the heart of a black hole, our laws of physics falter. General relativity, which describes gravity and the curvature of space-time, predicts the formation of the singularity. But it also signals its own failure there. Infinite density, infinite curvature. These are signs that a more fundamental theory is needed. Quantum mechanics, which governs the behavior of particles on the smallest scales, has no answer for what happens at the center of a black hole. The event horizon shields that mystery from view, locking it behind a veil that no signal can pierce. We know the black hole exists, but not what lies within. For decades, it was thought that black holes were simple, defined entirely by their mass, charge, and spin. They could swallow stars, gas, even light itself, but they gave nothing back, just a dark gravitational footprint. Then, in the 1970s, Stephen Hawking changed everything. Combining ideas from quantum field theory and general relativity, he showed that black holes aren't completely black. Instead, they emit a faint glow of particles, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where pairs of virtual particles pop into existence. One falls in, the other escapes. From far away, it looks as if the black hole is slowly evaporating. This was a revolutionary insight, but it led to a deep problem. As the black hole emits Hawking radiation, it loses mass. Over time, if no new matter falls in, it shrinks. Eventually, it may evaporate entirely, vanishing into a final burst of radiation. But here's the paradox. What happens to the information about everything the black hole once consumed? In quantum mechanics, information is never truly lost. The evolution of a closed system is reversible. The wave function evolves smoothly according to the Schrödinger equation. But in Hawking's picture, the radiation is completely thermal. It carries no imprint of the black hole's internal contents. If the black hole disappears, and the information is not encoded in the radiation, then it is lost forever. This violates one of the core principles of quantum theory. It sparked what has become one of the most profound puzzles in theoretical physics, the black hole information paradox. How can we reconcile Hawking radiation, which seems to destroy information, with a universe that, at its most fundamental level, should conserve it? The stakes are enormous. If information can be lost in black holes, then quantum mechanics itself may be incomplete. If it cannot, then something about our understanding of black holes, or space-time, must change. And the paradox only deepens the more closely we look. One of the most surprising developments in black hole physics was the realization that black holes have entropy. In classical physics, entropy is a measure of disorder, or more precisely, of the number of microscopic configurations that correspond to a given macroscopic state. A glass of water has entropy. A star has entropy. But a black hole? It seemed too simple. Defined only by mass, spin, and charge, it lacked the internal degrees of freedom that give rise to entropy. And yet, Hawking's work, along with that of Jacob Bekenstein, revealed that black holes must have entropy proportional to the surface area of their event horizon, not their volume. This was a profound shift. It suggested that information content in a black hole scales with its boundary, not what's inside, but what lies on the edge. Bekenstein's formula, later refined by Hawking, shows that the entropy of a black hole is proportional to the area of the event horizon, divided by the Planck length squared. That means the entropy of a black hole is immense, far greater than that of ordinary matter of the same mass. This connection between area and entropy led to the holographic principle, the idea that the fundamental description of a region of space may be encoded on its boundary, like a hologram. But understanding exactly what those microstates are and how they store information requires a theory of quantum gravity. General relativity describes black holes as smooth geometrical objects, while quantum mechanics demands a granular probabilistic structure. Reconciling the two requires a deeper framework, one that can describe space, time, and information on the smallest possible scales. Several approaches have tried to bridge the gap. In string theory, black holes can be modeled using collections of strings and branes, whose quantum configurations match the expected entropy. Loop quantum gravity, another candidate theory, describes spacetime as a network of discrete loops, which might account for black hole microstates in a different way. But no theory has yet emerged as definitive, and the paradox remains. One proposed resolution is that the information is somehow encoded in the Hawking radiation after all, that it's not truly thermal, but subtly entangled with the interior of the black hole. As the black hole evaporates, quantum correlations might allow the information to escape in a scrambled but recoverable form. This would preserve unitarity, the rule that quantum evolution is reversible, and save the foundations of quantum theory. But it raises new questions. How does the information get out? Through what mechanism? And if it escapes, does that violate the idea that nothing can travel faster than light? To address this, some physicists proposed a dramatic possibility, the firewall hypothesis. According to this idea, the smooth horizon of a black hole is an illusion. Instead, an infalling observer would encounter a wall of high-energy radiation, a firewall, at the horizon, where quantum entanglement breaks down. This would allow information to escape, but at the cost of violating another cherished principle of physics, the equivalence principle, which says that free fall through empty space should feel smooth and uneventful. The firewall proposal preserves unitarity, but only by sacrificing general relativity's core symmetry. It's a bold move, and one that remains highly controversial. Some researchers view firewalls as a sign that we've reached the limits of our current framework. Others see them as an artifact of overly strict assumptions. But all agree, the resolution to the black hole information paradox will likely involve new physics, perhaps even a new understanding of what space, time, and information really are. Despite their mystery, or perhaps because of it, black holes have become invaluable tools for physicists. They are not just astrophysical curiosities, they are crucibles where the known laws of nature are pushed to their breaking point. In the intense gravity near a black hole's event horizon, time slows. Space stretches. Tidal forces grew strong enough to rip apart atoms. These are the most extreme conditions the universe naturally provides, conditions that cannot be replicated in any laboratory on Earth. Studying black holes allows us to test general relativity in its most extreme regime and probe the edge of quantum physics where our current understanding begins to crack. In that way, every black hole is a natural experiment, a cosmic laboratory in which space and time are distorted beyond ordinary recognition. We can't peer into the singularity itself, but we can observe the behavior of matter and light near the event horizon. We can measure the orbits of stars around black holes, as has been done at the center of the Milky Way, where a supermassive black hole named Sagittarius A** anchors our galaxy. We can study the accretion disks of hot gas swirling around black holes, emitting X-rays and high-energy radiation. And now, with the advent of gravitational wave astronomy, we can detect the ripples in space-time caused by the collisions and mergers of black holes, signals that carry information directly from the most violent events in the universe. These observations provide essential data points, but the deeper conflict remains. Black holes sit at the intersection of two great but incompatible theories. Quantum mechanics describes the probabilistic behavior of particles and fields on the smallest scales. It has been tested with exquisite precision. General relativity describes gravity as the curvature of space-time, and it has passed every observational test in the macroscopic world. But when we try to combine the two, especially in extreme environments like black holes, contradictions arise. The information paradox is one example. Singularities are another. And the failure to describe what happens inside a black hole shows that neither theory, on its own, is complete. This incompatibility has driven the search for a theory of quantum gravity, a unified framework that can describe all forces, all particles, and all scales. String theory and loop quantum gravity are leading candidates, but they remain mathematically complex and difficult to test. Holography, inspired by black hole entropy, offers another promising path. According to the ADS-CFT correspondence, a duality proposed in string theory, a gravitational theory in a higher dimensional space, can be equivalent to a quantum field theory without gravity on its tail. Boundary. In this picture, a black hole in one universe corresponds to a quantum system in another, where information is preserved. This holographic principle has become a powerful tool for studying quantum gravity in highly symmetric spacetimes. Even if this specific duality doesn't apply to our universe directly, it suggests that space and time may be emergent, not fundamental ingredients of reality, but macroscopic effects that arise from being. Deeper quantum structures. In such a view, black holes might not be puzzles within spacetime, but clues to how spacetime itself comes into being. And so, black holes continue to illuminate the deepest fault lines in physics. They demand that we confront the paradoxes we'd prefer to ignore. They blur the lines between known and unknown, between the classical and the quantum. And they hint, perhaps more clearly than any other object, that the universe is governed by principles we have not yet fully grasped. At the forefront of black hole research, new ideas continue to challenge our assumptions, and sometimes our imaginations. One avenue explores quantum entanglement as a possible bridge between the interior and exterior of a black hole. The so-called ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, wormholes, and quantum entanglement may be two sides of the same coin. In this picture, particles that are entangled may be connected by tiny wormholes, and a black hole's interior could be related to the entangled structure of the Hawking radiation it emits. It's an elegant idea, though still speculative, and it hints that space-time geometry and quantum information may be more deeply intertwined than we've realized. Elsewhere, physicists are revisiting the notion of complementarity, the idea that different observers may have different but equally valid descriptions of the same physical system. From outside, a black hole looks like a hot, radiating object with no visible interior. From the perspective of someone falling in, the event horizon is smooth, and nothing unusual happens upon crossing it. These views seem contradictory, but some theories suggest they can coexist, not through illusion, but through a deeper, unified description. What unites all these efforts is a shared recognition. Black holes are more than endpoints of gravitational collapse. They are crucibles of fundamental truth, places where the known laws of physics bend and where new ones are forged. Whether through string theory, holography, quantum information, or yet undiscovered principles, the study of black holes is guiding us toward a more complete picture of the universe. One that will not only resolve paradoxes, but perhaps explain what space, time, and reality themselves are truly made of. At the heart of modern physics lies a deep and unresolved tension. Quantum mechanics and general relativity are two pillars of scientific understanding. Each has been tested again and again, and each has proven remarkably successful in its own domain. Quantum theory governs the tiny world of particles and fields, where uncertainty and probability rule. General relativity describes the vast architecture of space, time, and gravity, where matter tells space-time how to curve, and curvature tells matter how to move. But when the two theories meet, in extreme conditions like black holes or the earliest moments of the universe, they clash. The rules of one break the framework of the other. They cannot both be entirely correct. This is the problem of quantum gravity: to find a theory that unites these two descriptions into a coherent whole. Not a patchwork, not a truce, but a single, self-consistent framework that reveals how space-time behaves at the smallest possible scales. It's not just a mathematical exercise. Without quantum gravity, we cannot fully understand the origin of the cosmos, the fate of black holes, or the true nature of space and time. It is one of the deepest unsolved problems in all of physics, and perhaps the most fundamental. One of the most ambitious and mathematically rich approaches to quantum gravity is string theory. In this framework, the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. Different vibrational modes of the string correspond to different particles: an electron, a photon, a graviton. One of the great strengths of string theory is that it naturally includes gravity. The graviton, a hypothetical quantum of the gravitational field, emerges from the theory without being inserted by hand. String theory also unifies the other fundamental forces, suggesting that all interactions may arise from a single underlying principle. But there's a catch. For the equations to work, string theory requires extra dimensions, not just the familiar 3 of space and 1 of time, but 10 or even 11 dimensions in total. These extra dimensions must be curled up or compactified at scales far smaller than atoms, hidden from view. There are also many possible ways to shape and fold these dimensions, each giving rise to different low-energy physics. This leads to the so-called string landscape, a vast range of possible universes, each consistent in its own right. Some physicists see this flexibility as a strength. Others see it as a lack of predictive power. An alternative to string theory is loop quantum gravity, a non-string-based attempt to quantize space-time itself. In this approach, space is not continuous, but composed of tiny, discrete units, loops of quantum geometry. These loops form a network, or spin foam, which evolves over time according to specific quantum rules. In this view, space and time are not smooth backdrops, but emergent properties arising from the underlying quantum structure. The equations of general relativity emerge in the large-scale limit, just as thermodynamics emerges from the motion of molecules. Loop quantum gravity has had success in describing certain features of black holes and the early universe, including singularity resolution in some cosmological models. But it remains incomplete and difficult to test. Both theories, string theory and loop quantum gravity, are powerful, elegant, and speculative. Neither has yet been confirmed by experiment. Each offers a different glimpse of what quantum gravity might look like. But both share a common goal: to understand how the smooth fabric of spacetime emerges from something deeper, something granular and strange. At the heart of quantum gravity lies a fundamental question. Is space continuous, or is it made of discrete units? In general relativity, space and time form a smooth, continuous fabric. But quantum mechanics suggests that, at very small scales, this smoothness must break down. The Planck length, about 1.6 times 10^3 meters, is thought to be the smallest meaningful unit of distance. Below this scale, quantum fluctuations in geometry become so intense that space itself loses its classical meaning. Distances blur. The very notion of where begins to dissolve. Time, too, may not flow smoothly, but emerge from more fundamental quantum processes. This leads to a radically different picture of reality, one in which space and time are not fundamental, but emergent. In some theories, space-time is composed of tiny units, quanta of geometry, much like matter is composed of atoms. In loop quantum gravity, these units take the form of spin networks, which define areas and volumes with discrete spectra. In string theory, the granular structure emerges from the vibrations and interactions of strings and branes. In causal set theory, spacetime is modeled as a series of discrete events connected by causal relationships. In all cases, the smooth continuum of general relativity is an approximation, a large-scale limit of something more fundamental and quantum. But probing these ideas experimentally is extraordinarily difficult. The Planck scale is so far beyond the reach of today's particle accelerators that direct tests are effectively impossible. Even the Large Hadron Collider, the most powerful accelerator ever built, operates at energies more than 1 trillion times too low. But physicists have grown creative, turning to indirect clues. For example, quantum gravity might cause tiny violations of Lorentz invariance, the principle that the laws of physics are the same for all observers. These violations could leave imprints in high-energy cosmic rays or the polarization of light from distant gamma-ray bursts. Another potential window is the cosmic microwave background. The early universe was dense and hot enough that quantum gravity effects might have left subtle fingerprints in its fluctuations. Patterns in the polarization, non-Gaussianities, or unexpected correlations might offer clues. Similarly, gravitational waves, especially those from the early universe, could carry signatures of quantum space-time structure, though detecting them requires levels of sensitivity we haven't yet achieved. Some researchers also study black holes for experimental insight, hoping to detect echoes in gravitational wave signals from merging black holes, tiny deviations from classical predictions that might hint at quantum corrections near the event horizon. Still, most evidence remains theoretical, deeply mathematical, but not yet observable. This hasn't deterred physicists. Quantum gravity is not just about building machines, it's about building conceptual frameworks that push the limits of coherence and consistency. Even without experiments, theoretical tools like holography, dualities, and renormalization have deepened our understanding of quantum fields, thermodynamics, and the nature of space-time itself. In doing so, they help illuminate the contours of a theory we have not yet completed, but one we believe must exist. And when it does, it will not just unify the forces. It may reshape our understanding of what the universe is. Everywhere we look in the universe, we see matter. Galaxies, stars, planets, dust, gas, all made of atoms. And atoms are made of protons, neutrons, and electrons, particles of matter. But here's the puzzle. According to our best theories of the early universe, matter shouldn't exist in this abundance. In fact, it shouldn't exist at all. When energy condenses into particles, it should create matter and antimatter in equal quantities, a proton and an antiproton, an electron and a positron, side by side. But if that had happened perfectly, those particles would have annihilated each other, leaving behind only radiation. No galaxies, no atoms, no people. Yet somehow, in the earliest moments of the universe, a subtle imbalance occurred, a tiny excess of matter over antimatter. For every billion pairs of matter and antimatter, there was one extra particle of matter. That tiny difference was enough. The rest annihilated into light, but the leftovers formed everything we see today. This process, the origin of the asymmetry between matter and antimatter, is known as baryogenesis. And it remains one of the most profound and unsolved questions in modern physics. Why was there more matter than antimatter? What broke the symmetry? The search for answers begins with CP violation, a subtle breakdown in the symmetries of nature. In physics, the combination of charge conjugation and parity transformation describes how particles behave when flipped into their mirror image opposites and exchanged with their antiparticles. If the laws of physics were perfectly symmetric, CP would hold, meaning that matter and antimatter would behave identically under mirror reflection and charge reversal. But experiments have shown this isn't quite true. In certain decays of subatomic particles, like kaons and B mesons, the probabilities differ slightly for matter and antimatter. This violation of CP symmetry is one of the few known ingredients capable of generating a matter-dominated universe. However, the CP violation observed so far is too small to account for the matter-antimatter imbalance we see today. The standard model of particle physics includes CP violation, but not enough of it. This suggests that new physics must exist, processes or particles beyond the standard model that produced stronger asymmetries in the early universe. One leading theory is electroweak baryogenesis, which proposes that during the electroweak phase transition, when the electromagnetic and weak nuclear forces separated, certain interactions favored the creation of matter. These would require new particles and forces, potentially observable at high-energy colliders. Another possibility comes from leptogenesis, a theory in which the asymmetry begins not with baryons, but with leptons. In this scenario, heavy right-handed neutrinos, particles not included in the standard model, decay in a way that violates CP symmetry, creating more leptons than antileptons. These lepton asymmetries are then converted into baryon asymmetries through interactions predicted by the standard model at very high energies. Leptogenesis is particularly attractive because it also helps explain the tiny masses of ordinary neutrinos, which are otherwise difficult to account for. Both electroweak baryogenesis and leptogenesis offer promising frameworks, but they remain unconfirmed. They depend on physics we have not yet observed, new particles, new interactions, new energy scales. And so the mystery continues. Why, in a universe that should have produced equal amounts of matter and antimatter, are we here at all? To uncover the origins of the matter-antimatter asymmetry, scientists have turned to some of the most precise tools ever built: particle accelerators. At facilities like the Large Hadron Collider and Japan's SuperCAB accelerator, researchers study rare particle decays in exquisite detail. One focus is on B mesons, short-lived particles containing a bottom quark, which exhibit CP violating behavior. By comparing how B mesons and their antiparticles decay, physicists can measure the tiny differences that hint at symmetry breaking. These measurements test the limits of the standard model and search for deviations that might point to new physics. So far, the results have confirmed the presence of CP violation, but again, not enough to explain the cosmic imbalance. Still, these experiments help narrow the search. They constrain the properties of potential new particles and interactions that might exist at higher energies or in hidden sectors. Some theories suggest that heavier versions of the Higgs boson or undiscovered particles related to supersymmetry could amplify CP violation during early universe transitions. Others predict that the asymmetry might be tied to new forces that couple differently to matter and antimatter, leaving subtle traces in decay channels or mass differences that future colliders could detect. Beyond accelerators, scientists are exploring the symmetry of nature itself, looking for violations of the most basic assumptions about particles and their mirror twins. One striking approach involves searching for the electric dipole moment of fundamental particles like the neutron or electron. If these particles have an intrinsic asymmetry in their charge distribution, it would signal a violation of two-reversal symmetry and, by extension, CP symmetry. Experiments using ultra-cold neutrons and precision atomic clocks have pushed the limits of EDM detection to astonishing precision. So far, no non-zero EDM has been observed, but the constraints keep tightening, ruling out broad classes of models. Meanwhile, theorists continue to investigate what might have happened in the earliest instance of time, just fractions of a second after the Big Bang. At that moment, the universe was a seething plasma of quarks, gluons, leptons, and radiation. Temperatures and energies were far beyond anything we can recreate in a laboratory. But in that chaos, small imbalances could have profound consequences. Some models suggest that the asymmetry arose through spontaneous symmetry breaking, a kind of phase transition, like water freezing into ice, where different regions of the universe fell into slightly different states. If those states favored matter in some regions and antimatter in others, the resulting dynamics could leave behind a matter-dominated cosmos. In these scenarios, topological defects like domain walls or cosmic strings might have formed, exotic structures in spacetime where symmetry breaking was incomplete or varied. These structures could serve as catalysts for baryogenesis, concentrating CP violating processes and magnifying their effects. While there's no direct evidence for such defects, they remain an intriguing possibility, one that connects high-energy particle physics with the large-scale evolution of the cosmos. Alternatively, other mechanisms invoke interactions with inflation fields, the hypothetical energy fields that drove inflation, or draw on ideas from string theory and extra dimensions. Each proposal offers a different route to the same destination, a universe made of matter. And while none has yet been proven, they remind us that the origin of matter is not a solved problem. It's a frontier, one where theory and experiment still struggle to meet, and where the most basic question of all remains open. The consequences of the matter-antimatter asymmetry are written across the entire structure of the universe. Because a tiny excess of matter survived the primordial annihilation, the cosmos was left with enough material to form hydrogen and helium during Big Bang nucleosynthesis. Those elements seeded the first stars, which forged heavier atoms through nuclear fusion and supernova. From those atoms came planets, molecules, life. The very existence of galaxies, from dwarf spheroidals to massive spirals, rests on that 1 in a billion imbalance, established in the universe's first moments. If the symmetry had been exact, the universe would have ended in a sea of photons, hot, dense, and utterly sterile. The cosmic microwave background still bears the imprint of this ancient violence. It shows a nearly perfect blackbody spectrum, but with tiny fluctuations, ripples in temperature and density, that later grew into galaxies and clusters. These fluctuations reflect the behavior of matter in the early universe, and their very presence implies that some matter survived while antimatter did not. Even today, the distribution of matter is uneven, but the antimatter component is essentially absent. Searchers for large regions of antimatter, anti-galaxies, anti-stars, or anti-planets have found no compelling evidence. If such structures existed, we would expect to see intense gamma-ray signatures where matter and antimatter meet, annihilating in bursts of energy. But the sky is quiet. Antimatter is produced in small amounts in high-energy processes, such as cosmic rays or particle accelerators, but these are transient, not signs of antimatter worlds. The visible universe appears to be made of matter, and only matter. And yet, for all its observable consequences, the origin of the asymmetry remains elusive. None of the known mechanisms within the standard model of particle physics can explain the magnitude of the imbalance. The CP violation observed in meson decays is real, but too weak. The model contains no heavy neutrinos, no extended Higgs sector, and no natural phase transition strong enough to drive efficient baryogenesis. This shortfall is one of the strongest arguments for physics beyond the standard model, a sign that what we call complete is missing critical pieces. Some theorists have proposed entirely new classes of interactions. One possibility is that baryon number, the total number of baryons like protons and neutrons, is not conserved in the early universe. Grand unified theories, which attempt to merge the strong, weak, and electromagnetic forces into a single framework, often predict baryon-violating interactions mediated by extremely heavy particles. These interactions could naturally generate an asymmetry if they also violate CP symmetry and occur out of thermal equilibrium, 3 criteria laid out by the physicist Andrei Sakharov in 19BF. 67. His Sakharov conditions remain the foundation for all baryogenesis models. But detecting these processes directly is another matter. The energy scales involved, often near 10 to the power of 16 giga-electronvolts, are far beyond the reach of current experiments. Even indirect signatures, like proton decay, have yet to be observed, despite decades of searching. Still, the absence of evidence doesn't mean the evidence is absent. It may simply lie just beyond the horizon of our instruments, waiting for more sensitive detectors, deeper sky surveys, or more imaginative theories to bring it into view. In many ways, the question of matter-antimatter asymmetry is also the question of why anything exists at all. The laws of physics, as we know them, are largely symmetric. For every particle, there is an antiparticle. For every force, an equal and opposite reaction. And yet, the visible universe is not a place of perfect balance. It is lopsided, tipped ever so slightly toward matter. That tipping is what made galaxies possible. It made atoms possible. It made you possible. Without it, the universe would be empty of structure, empty of chemistry, and utterly devoid of life. This makes the asymmetry not just a scientific puzzle, but a condition of existence. We often take the presence of matter for granted, but it is, at its core, an extraordinary stroke of cosmic luck, or perhaps a signal of deeper principles not yet revealed. The laws that governed the earliest moments of time did not merely permit the survival of matter they selected for it. They pushed the universe away from perfect symmetry toward a future where stars could burn, where molecules could form, and where observers like us could ask why. And so the search continues, not just to explain a ratio or a decay pattern, but to understand the most basic question physics can ask. Why is there something rather than nothing? Whatever the answer may be, it will reach far beyond particle physics. It will touch the origin of matter, the fate of the universe, and the delicate conditions that made a thinking, wandering species possible, one capable of looking out at the stars and asking, with quiet awe, why it is here at all. For most of human history, the word universe meant everything. All of space, all of time, all of existence, a single, coherent whole. But in modern physics, that idea has begun to unravel. What we call the universe may be just one bubble in a much larger cosmic sea. Beyond the edge of what we can observe, other regions may exist, perhaps governed by different laws, shaped by different constants, structured in ways we can barely imagine. Together, they form what many now call the multiverse, a grand ensemble of universes, with ours as merely one example. It's a radical idea, but it didn't begin as speculation. It began with inflation. In the 1980s, cosmologists confronted a series of puzzles in the Big Bang model. Why is the universe so flat when curvature should dominate over time? Why is the cosmic microwave background so uniform when distant regions should never have been in contact? And why are there no magnetic monopoles or other exotic relics predicted by early universe physics? The solution, proposed by Alan Guth and others, was cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. During this phase, space expanded faster than the speed of light, not in violation of relativity, but as a property of space-time itself. This rapid inflation smoothed out curvature, stretched quantum fluctuations into cosmic structures, and diluted unwanted relics to invisibility. It also made distant regions of the universe causally connected before inflation began. The result was a cosmos that looked flat, homogeneous, and isotropic, just as we observe. Inflation solved many problems at once, and it has become a foundational part of modern cosmology. But inflation has its own implications, and one of them is the multiverse. In many models, inflation doesn't end everywhere at once. It ends in some regions, creating bubble universes like ours, while continuing in others. This process, known as eternal inflation, leads to a self-replicating cosmos, an infinite fractal of inflating space, constantly spawning new regions with their own physical conditions. Some bubbles may contain laws similar to ours, others may be wildly different. In this picture, the Big Bang wasn't the beginning of everything, just the beginning of our local patch. And because inflation wipes clean any evidence of what came before, we cannot see beyond our cosmic horizon. This makes the multiverse difficult to test directly. Each universe is causally disconnected from the others, meaning light from outside our region will never reach us. But the idea arises naturally from well-motivated physics. It's not an add-on or a fantasy. It's a prediction of equations already in use, of scalar fields, vacuum energy, and quantum fluctuations in an inflating spacetime. The multiverse may not have been the goal, but it seems to be the destination. And if the laws of physics differ from one bubble to the next, then our own universe, with its specific constants and delicate structures, might be just one possibility among many. There's not just one kind of multiverse. In fact, modern physics proposes several distinct versions, each emerging from different branches of theory. One is the inflationary multiverse, countless bubble universes spawned by eternal inflation, each with its own local laws and constants. Another comes from quantum mechanics, the many worlds interpretation. In this view, every quantum event with multiple outcomes causes the universe to branch, creating parallel histories where every possibility is realized. A third type appears in string theory, where the enormous landscape of possible vacuum states could give rise to different universes embedded in extra dimensions. Each model offers a different answer to what lies beyond the boundaries of observation. In the inflationary multiverse, space itself continues to expand chaotically. Our observable universe is just one calm pocket where inflation has ended and standard cosmological evolution has taken over. In the quantum multiverse, reality splits constantly, creating a web of diverging timelines, one for every dice roll, every electron spin, every branching path. And in the string landscape, the laws of physics depend on how extra dimensions are compactified, curled up in tiny, intricate shapes that determine everything from particle masses to force strengths. With as many as 10 to the 500 possible configurations, the number of potential universes is beyond astronomical. To many physicists, this variety is not a flaw, but a feature, one that may help explain an ancient mystery: why our universe appears so perfectly tuned for life. The fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton, the density of dark energy, all fall within a narrow range that allows complex structures to form. A slight increase in the cosmological constant would prevent galaxies from coalescing. A slightly stronger strong nuclear force might bind protons so tightly that fusion in stars would never ignite. A weaker electromagnetic interaction might prevent atoms from forming at all. This fine tuning has puzzled scientists and philosophers alike. Why are the numbers just right? One answer is anthropic selection. We observe this universe because it's one of the rare regions where life is possible. In a multiverse with countless variations, most regions would be sterile, too chaotic, too short-lived, or governed by laws hostile to complexity. But in a few patches, the constants fall into the narrow range that permits atoms, chemistry, stars, and observers. We find ourselves in one of those patches, not because it's the only one, but because it's the only one we could be in. The cosmological constant problem is a particularly striking case. Quantum field theory predicts that empty space should have a vacuum energy density many orders of magnitude larger than what we observe. The value measured through cosmic acceleration is not zero, but it's extremely small and just barely large enough to influence the expansion of the universe. In most versions of the multiverse, vacuum energy varies from one region to the next. So again, the anthropic principle may apply. Only those regions where the cosmological constant is small enough to allow galaxy formation would be observed. It's not a satisfying answer for everyone, but it may be the only one that fits both the data and the theories we have. Not everyone accepts the multiverse as a scientific idea. The core issue is testability. Science, at its heart, relies on falsifiability, the ability to confirm or refute a theory through observation or experiment. But if other universes are forever beyond our cosmic horizon, unreachable by light or signal, then how can we ever verify their existence? Some critics argue that the multiverse, while mathematically consistent, belongs more to metaphysics than to physics. It may be a useful tool for interpreting theories, but without observable consequences, it risks becoming a story we cannot prove. Elegant, yes, but unverifiable. Others disagree. They argue that the multiverse is not a theory unto itself, but a consequence of theories we already use. Inflation, string theory, and quantum mechanics all point toward multiverse-like behavior under reasonable assumptions. If those theories are tested and supported by data in other ways, then their logical consequences, including the multiverse, must be taken seriously. For example, if future experiments reveal particles predicted by string theory, or if we confirm specific features of inflation through the cosmic microwave background, then the idea of multiple universes may gain indirect support, even if we never observe another universe directly. Some even propose that traces of other universes might exist in subtle ways. In models of bubble collisions during inflation, two universes could, in theory, collide at their edges, leaving imprints in the cosmic microwave background, perhaps as circular anomalies or slight temperature distortions. So far, no such evidence has been found. But searches continue, and future observations with more sensitive instruments may reveal clues. It's a long shot, but one physicists haven't yet ruled out. Still, the debate runs deep, not just among physicists, but among philosophers of science. At its core, the multiverse challenges our notion of uniqueness. If the laws of physics vary across different regions, then what we call fundamental constants may not be fundamental at all, merely local facts. Our theories may describe only a small piece of a much larger landscape, with no single elegant solution that governs everything. This is a sharp departure from the traditional dream of physics, that all of nature could be explained by a simple, universal set of laws. The multiverse also reopens questions about contingency and necessity. Why does the universe have these laws, these particles, these dimensions? In a multiverse, the answer may be that it doesn't have to, that all possible variations exist somewhere, and we happen to be in one that permits our form of complexity. This undermines the idea of a final theory, one uniquely determined by mathematical or logical necessity, and replaces it with a vast probabilistic mosaic of possibilities. And then there is the question of meaning. In a multiverse with infinite worlds, every outcome happens somewhere. Every history plays out. Every version of you, every decision, every accident, every life, all realized in some distant pocket. Does this diminish the significance of our choices? Or does it expand our perspective, reminding us that even in a vast and indifferent cosmos, the version we experience still matters? These are not questions with simple answers, but the multiverse invites us to ask them, and to consider that the universe may be far stranger and far richer than we ever dared to imagine. As the idea of the multiverse continues to evolve, it opens more questions than it answers. What determines the distribution of universes, their laws, constants, and geometries? Is there a deeper principle, a hidden rulebook that governs the multiverse as a whole? Or is it purely stochastic, governed by chance and quantum fluctuations, with no ultimate design? And if the multiverse is real, how do we define probability in an infinite landscape where everything that can happen does? These are not just mathematical curiosities. They touch the foundations of cosmology, quantum theory, and even logic itself. Some theorists are exploring measure problems in eternal inflation, ways to define meaningful probabilities in a multiverse where every outcome occurs infinitely many times. Others study how initial conditions, vacuum selection, or cosmological constants might emerge from deeper laws, perhaps via quantum cosmology, causal set theory, or holographic dualities. There is even speculation that information from one universe might subtly influence another through quantum entanglement or topological structures, though these ideas remain highly speculative and untested. And yet, in spite of all the unknowns, the multiverse continues to shape the frontier of physics. It pushes us to reconsider what counts as science, what counts as explanation, and what it means to understand the cosmos. Whether it turns out to be true or not, the very act of grappling with these ideas reveals something essential about human inquiry: our refusal to stop at what's seen, our urge to press against the edge of the knowable. Because just beyond the horizon of our universe, there may be more than space and time. There may be a vast ocean of possibilities, still waiting to be imagined. Maybe you're still awake, or maybe you're already floating somewhere deeper, letting the last few thoughts dissolve into silence. Either way, it's okay. The universe doesn't mind if you missed a detail or drifted off halfway through a thought. It will still be here, quiet, steady, full of questions. And that's what makes it such a gentle companion. It asks nothing of us. It simply unfolds. Tonight, we traced the outlines of mysteries, soft as shadows. Not to solve them, but to feel their shape. Dark matter that we can't see, yet feel in the way galaxies move. Dark energy that pulls the stars apart in silence. Black holes where space turns inward and time slips through. The strange dance of particles and probabilities. The quiet asymmetry that lets us exist. And beyond it all, perhaps, other worlds. Unreachable, unknowable, but not unthinkable. There's comfort in not knowing, in accepting that the universe doesn't always explain itself right away. And in that quiet, we can rest. Maybe your breath has slowed. Maybe your limbs feel heavier. Maybe the questions have begun to fade into the background, like stars behind a clouded sky. Let them fade. Let your thoughts stretch wide and weightless. The science will wait for you tomorrow or next week, or some other gentle night. Sleep doesn't mean you missed the story. It means you've become part of it. Because this too is part of science. The quiet moments, the stillness, the curiosity that continues even as we close our eyes. A kind of dreaming that asks, not for answers, but for wonder. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.